Okay. So in those hand warmers in the Florence flask, we were looking at a supersaturated solution of sodium acetate. Now sodium acetate is NaCH3CO2. This is the sodium part. This is the acetate ion. Okay? And what happens is you've got sodium acetate that is dissolved in water. And so in that water, then we've got sodium ions, and we've got acetate ions.
Sodium acetate.
What is it?
Yeah.
It's just a chemical salt. You can actually make it at home. Okay. So the way that we got the solid that you have in there now to dissolve and form a supersaturated solution was to add heat. So what Thomas is doing back there is he's putting those in the beakers. You put about 2 or 3 of them in a beaker. If there's not enough water to cover the top, we're going to have to put a little more water in there. And then he's going to turn it on and let it heat up to near boiling and let it sit like that for a little while, and it'll go back to being in solution. Okay, so here's what's happening. As we heat this up, we break the bonds that's holding the sodium acetate crystals together, and they become solvated. And then when we cool it down and create a supersaturated solution, then when these things come out of the solution and form the solid, they give off the same heat they took in. So we're putting heat into the system to get it to dissolve. Then we're getting the heat out when we take them out of solution. Okay? Mm-hmm.
Mr. Tennant?
Yep.
Is that CH3CO2?
Yes. 2 up here, right? 2. Okay? All right. So, now look. There's a single ionic bond between these ions right here. A single ionic bond between these ions here. And what this shows you, this is a demonstration of something that doesn't come up until Unit 10. It's called thermochemistry or thermophysics or whatever we're doing here. But this is a process of adding heat to an equation. So heat now becomes part of the equation. Energy becomes part of the equation. Okay? And what we're actually demonstrating by showing this is, since what happens when you snap that little button, or when we put that little crystal into the Florence flask, there was heat given off, and then to get them to separate, you have to add heat. When that formation of bonds occurs, the main thing that's happening here is formation of bonds. Formation of bonds is always exothermic. Exothermic means giving off heat. Formation of bonds is always exothermic. Okay? So I could write this equation as Na plus CH3CO2 negative becoming NaCH3CO2 solid plus heat. Okay? We could actually make heat part of the equation. All right? Bond formation is always exothermic. Okay? Now, solvation, that is surrounding these particles with water, we talked about yesterday, can also either take in or give off heat. The actual solvation process is exothermic. On the other hand, breaking the particles away from their crystal is endothermic. So when the solvation process gives off heat, when the solvation process itself gives off heat, then surrounding the particles with water gives off more heat than is required to break them apart. So there's a give and take going on with a lot of these things. Okay? If you take calcium chloride, and in our containers over there on the left, we have 3 containers that contain different salts. We've got magnesium sulfate on the far left, sodium chloride in the middle, and calcium chloride on the far right. You can buy calcium chloride in department stores. You can buy it this time of year. You can buy it in hardware stores. This is things that melt ice. Okay? You can take calcium chloride and simply dissolve it in water and fill the cup. It gives off heat. Okay? And it gives off heat because surrounding those calcium and chloride ions with water molecules gives away a lot of heat. So the solvation process can give off heat. Okay? All right. Now that's kind of a look ahead at something that's coming up later in the semester. Right now I want to get back to the solution process itself, and I want to discuss very briefly this process of dissolving gases. We don't do that a lot, but you undissolve gases all the time when you drink a soft drink. Okay? So let's see, you got a soft drink. Okay, and there's a soft drink in here. And you pop the top, take the top off, what happens? Okay. So when you are holding this bottle before you take the top off, and then you hold the bottle after the top's taken off, does it feel any different? How does it feel different?
It feels relief.
Okay, so when the top's on, it feels tight. With the top on, there's pressure inside the bottle. When you take the top off, you can hear it go, psst, right? Yeah. So you release that pressure, and the gases start to come out. They start to do what? Evolve, evolution of gases. Okay? All right. So the point is this, that when the top is on here, the pressure of the gas that's dissolved is high. Higher pressure results in more dissolved gas. Okay? When you release the pressure, then the bubbling starts. The amount of gas you can dissolve is lowered. The amount of gas you can dissolve is lowered when you lower the pressure above it. Okay? So if the concentration of gas is, well, let's put it this way. If the pressure of the gas goes down, the concentration goes down. Okay? So that concentration divided by pressure is equal to a constant. This begins to look like something we had in the last unit, doesn't it? C1, P1, C2, P2. Okay? This is called Henry's Law. Okay, we're not going to do any calculations with Henry's Law. You just need to know that's what it is. You need to know basically kind of how it works. Okay? Another way this is often written is the solubility of a gas is directly related to the pressure of the gas above the liquid. So it's S1 over P1 equals S2 over P2. I can't write today. S1 over P1 equals S2 over P2. Okay? So the S just stands for solubility, C stands for concentration. Works about the same way. Okay? Any questions? All right. Temperature also affects the ability of gases and solids to dissolve. So here's our beaker again. Here's our solution. Okay? All right? If you increase the temperature of this solvent, if you increase the temperature of the solvent, if it's a solid you're dissolving, okay, then you also increase generally, not always, but generally, you also increase the solubility of solids. That's an S with a subscript S. Okay? If you increase the temperature, you increase the solubility of solids. Usually, typically, not every single time, but most of the time. Okay? Most of the time you can dissolve more solids if you increase the temperature. Okay? Just like I was able to dissolve more sodium acetate by increasing the temperature, just like we're doing right now. Okay? On the other hand, if we increase the temperature of a gas that's dissolved in a liquid, we're increasing the temperature, then the solubility of a gas is decreased, usually. Okay? So the opposite effect occurs. You can dissolve more solids in a higher temperature. You can dissolve less gas in a higher temperature. Okay?
So the solubility of a gas is decreased?
Yes. All right? So how many of you are fishermen? Like to go fishing? All right, this better be important to you. Okay? Where do you fish for trout? In a river?
In cold water.
Cold streams, usually. Fast running water. Because the cold water dissolves more gas, more oxygen in particular. Trout need a lot of oxygen. Okay? If the stream goes too slow, the trout can't live there. Okay? Now, if you have a small pond without a lot of oxygen in it, you get a lot of catfish. They can live with a lot less oxygen. But if it goes too slow and the temperature goes too high, then the catfish die. And you can only get little critters, little crawly critters on the bottom. Okay? And eventually, if you lose too much oxygen, even they die. Okay?
So how do they not get...
What? Well, this is a S for solid. This is a G for gas. Yep.
How do they get too much oxygen? Like,
I don't know of any case where they can get too much oxygen. Okay. However, what happens is, as you increase the amount of oxygen, you change the kind of fish that are there. And since the fish are the predators, they eat all the little creepy crawlers. Okay? So you reduce the number of creepy crawlers by increasing the amount of oxygen, which increases the predator fish.
What? That's what I'm asking. How do you increase the amount of oxygen?
Oh, decrease the temperature, and also increase how fast it moves around, because you dissolve more oxygen when it's moving around fast.
Like, if you have a pond, how would you, like, do the temperature?
You'd have something in there that stirs the water up, like in a fish tank.
Oh.
That's why you have one of those things that turn the water over in a fish tank. It dissolves more oxygen. Okay? If you have certain kinds of fish in a fish tank, sometimes you have to keep the water cold. Okay? That's how fish are able to live under the ice in a pond or a lake. Because the cold water holds the oxygen and allows them to survive under there. Okay? Otherwise, all the fish would die, wouldn't they? Right? So if you're a fisherman, this is the kind of chemistry you want to know about. All right? Now, those are general ideas. Not all gases dissolve more when you decrease the temperature. Not all solids dissolve more when you increase the temperature. Most of them do. Does that make sense? So get out your test references now. Get out your test references. And in your test references, you're going to have a graph which looks at solubility behavior for certain selected solids, particularly salts and gases.
I need to test references.
How many of those have I given you, Evan?
I haven't ever Jasmine.
Yep. I'm going to donate some money to the forestry department of South Carolina.
I know, you just...
What does it say right there? What does it say right there? Okay. So let's look at this chart a minute. Look at this chart. Okay. What would you say is the solubility, the maximum solubility of potassium nitrate at 40 degrees centigrade?
105.
Okay, let's see how you figure that out. I see potassium nitrate is this line right here. Okay?
Oh.
The temperature's down here. Did I say 40 degrees? 40 degrees is right here. So the maximum solubility of potassium nitrate at 40 degrees is going to be what? I think it's like 64, but that's a reasonable guess, okay? That makes sense? So you have to be able to interpret graphs, okay? Figure things out. But now I want you to look at all the lines on here. Look at all the lines on here. Let's do a summary. Okay, let's analyze the behavior of solids and gases. In general, you look at the way all these patterns occur. What can we say about the way that solids dissolve as you increase temperature, usually? As you increase temperature, what can we say about dissolving of solids? What can we say about dissolving these? Actually, the solid, the solubility goes up. We can dissolve these salts more as we increase temperature. Gases tend to go down. Okay, let's stick with the solids for a minute. Okay, are there any exceptions to solids increasing their solubility as you increase temperature? Ki goes up. It's just off the chart. NH3 is a gas. It's a dotted line.
No.
Na2SO4 goes down.
What about NaCl? It stays the same.
Well, it slightly goes up. It's not much, but it slightly goes up. The real exception here is this sodium sulfate right here. This line right there. Okay? But all the others go up. All the other solids go up and all the other gases go down. Okay, that's a really good summary, Amber. Good for you. Okay? And those are important concepts for you to know. But you know someone that you kind of know. How are you going to dissolve more sugar in your tea? Heat it up. Put the sugar in while it's still hot. Okay. Or put it in the fridge or something. All right, now we're going to start with some calculations. Nope, I didn't say that. All right, we said in the very beginning of this unit, well, let me change this over here. Stop capture. So this